Good afternoon. March the 19th, 2013. This is MATB110, Section 1, Conference 1. Today is date number 18, 8 to the semester, week number 9. So let's get started. Welcome back, and I hope you get a very good result in the midterm exam yesterday. Have you taken the midterm exam? No. Have you? No. What do you think? It's just like a quiz, right? But you have a lot of choices, so maybe the result turns out to be quite different. Just trying to get to the point of how you would choose the first set of questions towards the back of the questions. Basically, it's just like your quiz, and quiz is based on the exercise you do. Now, when we talk about exercise, remember, you have not been assigned an exact number of questions yet for the next assignment, the NA. You will see the questions by this Friday, okay? That means by the end of tomorrow. I'm still working out how many questions, maybe just 4 questions altogether. And the reason is because we have to cover something to make sure you understand it. Well, if we look at what we have been doing so far, I'm just deducting what we have given you from week number 8. And so when we come to week number 9, you see we have finished up to lecture number 11, which is on Monday's class. Okay, today is first day, so we are going to relate grades and Newton's methods and the sometimes. At the same time, I would like to introduce you something called the L'Hopital rule. We cannot cover all these in one class, but it's expected you to make the best use of those video resources as well as the notes, okay? Do not forget that each of this link here will give you the specific set of notes related to the problems there, and it's expected you study the notes together with the video. You see that we have kept the records of your learning from the very beginning, that is from week number 1. And I'm giving you the records towards the end of each week by use of the end of the week activity. So, well, after this particular month, 1 more month will be left for you to go through. Count this one which we're going to concentrate on, the integration part. And so if you look at things like this, we're getting ready for some of the things we're not covered from these small sections of the textbook, particularly the optimization problem, which come from section 3.6. You did 1 or 2 problems there, and I have already given you a consistent problem in your quiz and also in the midterm exam, and I do not know if you take advantage of it. Do you remember which one? It's the example, right? The example of the optimizations of the area. So today we're going to visit some of those optimization problems from the notes and explanations from Professor David Jefferson. Okay, so and after that I would like to save some time to make you understand the importance of this resource called Introductions to L'Hopital. Okay? Before we come back to do the mean value theory, not today, next Monday. So, let's go for it. Related grades, okay? Make sure you follow up with the examples given.
In the 12th lecture, we're going to talk about maxima and minima. Let's finish up what we did last time. We really only just started with maxima and minima, and then we're going to talk about related grades. So right now, I want to give you some examples of max-min problems. And we're going to start with a fairly basic one. So what's the thing about max-min problems? The main thing is that we're asking you to do a little bit more of the interpretation of word problems. So many of the problems are expressed in terms of words. And so in this case, we have a wire, which is length 1, cut into 2 pieces. And then each piece encloses a square. Sorry, encloses a square. And the problem, so this is the setup, and the problem is to find the largest area enclosed. All right, so here's the problem. Now, in all of these cases, there's a bunch of words, and your job is typically to draw a diagram. Okay? So the first thing you want to do is to draw a diagram. In this case, it can be fairly schematic. Here's your unit length, and when you draw the diagram, you're going to have to pick variables. So those are really the two main tasks to set up the problem. So you're drawing a diagram. This is like word problems of old in grade school through high school. Draw a diagram and name the variables. So we'll be doing a lot of that today. So here's my unit length, and if I'm going to choose the variable x to be the length of one of the pieces of wire, and that makes the other piece 1 minus x. And that's pretty much the whole diagram, except that there's something that we did with the wire after we cut it in half. Namely, we built two little boxes out of it, like this. These are our squares. And their side lengths are x over 4 and 1 minus x over 4. All right? So far, so good. And now we have to think, well, we want to find the largest area, so I need a formula for area in terms of the variables that I've described. And so that's the last thing. I'll pick a letter A as the label for the area. And then the area is just the square of x over 4 plus the square of 1 minus x. Whoops. Strange 2 over 4. All right? Okay, so far so good. Now, the instinct that you'll have, and I'm going to yield to that instinct, is we should try to have them just differentiate. All right? That's all right. We'll find the critical points. So we know that those are important points. So we're going to find the critical points. In other words, we take the derivative we said, the derivative of a with respect to x equal to 0. All right? So if I do that differentiation, I get well, so the first one, x squared over 16, that's 8. Sorry. That's x over 8, right? That's the derivative of this. And if I differentiate this, I get, well, the derivative of 1 minus x squared is 2 times 1 minus x times a minus 1. So it's minus 1 minus x over 8. Right? So there are 2 minus signs in there. I'll let you ponder that differentiation, which I did by the chain rule. All right? Hang on a second, okay? Just wait until we're done. All right, so here's the derivative. All right? Is there a problem? Well, so there's a 1/16 here. This is x squared over 16. And so it's 2x over 8. Well, over 16, sorry, which has 8. All right? Okay. That's okay. All right, so now, this is equal to 0 if and only if x is equal to 1 minus x, that's 2x is equal to 1, or in other words, x is a half. All right? So there's a critical point. So x equals a half is a critical point, and the critical value, which is what you get when you evaluate a at 1/2, is a half divided by 4, that's an eighth. Right, so that's an 8 squared plus a an 8 squared, which is 1 over 2. Right? So far so good. But we're not done yet. All right? We're not done. All right? So why aren't we done? Because we haven't checked the endpoints. All right? So let's check the endpoints. Now, in this problem, the endpoints are really sort of excluded. The ends are between 0 and 1 here. That's the possible lengths of the cut. And so what we should really be doing is evaluating in the limit. So that would be the right-hand limit as x goes to 0 of a. And if you plug in x equals 0, what you get here is 0 plus 1 over 4 squared, which is 1/16. All right, and similarly, at the other end, that's 1 minus 1 from the left. We get a quarter squared plus 0, which is also a 16. So what you see is that the schematic picture of this function, and this isn't even so far off from being the right picture here, is that its level here is 16, and then it dips down and goes up. Right? This is a half, this is 1, and this level here is a half. This is a 1 over 32. All right? So we did not find, when we found a critical point, we did not find the largest area closed. We found the least area closed. So if you don't pay attention to what the function looks like, not only will you about half the time get the wrong answer, you'll get the absolute worst answer. You'll get to one which is the polar opposite from what you want. All right? So you have to pay a little bit of attention to the function you've got. And in this case, it's just very schematic. It dips down and goes up. And that's true of pretty much most functions. They're fairly simple. I mean, you only have one critical point. You only turn around once. But then maybe the critical point is the maximum, or maybe it's the minimum. Or maybe it's neither, in fact. So we'll be discussing that maybe some other time. All right, so what we find here is that we have the least area enclosed is the 32nd, right? And this is true when x equals 1/2. So these are equal squares. All right? And most when there's only one square. Which is more or less the limiting situation if one of the pieces disappears. All right? Now, so that's the first kind of example. And I just want to make one more comment about terminology before we go on. And I will introduce it with the following question. What is the minimum? All right? So what is the minimum? Yeah. Right, the lowest value of the function. So the answer to that question is 1 over 32. Okay? Now the problem with this question, and you will, so that refers to the minimum value. Right? But then there's this other question, which is where is the minimum? And the answer to that is x equals 1/2. Okay? So one of them is the minimum point and the other one is the minimum value. All right, so they're two separate things. Now, the problem is that people are sloppy, and especially since we usually find the critical point first, and the value that is plugging in for A second, people will stop short, and they'll give the wrong answer to the question, for instance. Now, both questions are important to answer. You just need to have a word to put there. So this is a little bit careless. When we say what is the minimum, some people will say half. And that's literally wrong. They know what they mean, but it's just wrong. And when people ask this question, they're being sloppy anyway. They should maybe be a little clearer and say what's the minimum value, or where is the value achieved? It's achieved at, or where is the minimum value achieved? Where is in achieved would be a better way of phrasing this second question so that it has an unambiguous answer. And when people ask me for the minimum point, they're also, well, so what is what we call the minimum point? We have this word critical point, which is what examples I have is in critical value. And so I'm making those same distinctions here. But there's another notion of a minimum point. And this is an alternative, if you like. The minimum point is the point a half 1/32. Right? That's a point on the graph. It's the point, well, so that graph is way up there, but I'll put it on there. That's this point. And you might say min. Yeah, you might point to this point and you might say max. And similarly, this one might be max. Okay? So, in other words, so what this means is simply that people are a little sloppy, and sometimes they mean one thing and sometimes they mean another. All right? And you're just stuck with this because there will be some authors who will say one thing and some people will mean another, and you just have to live with this little bit of annoying ambiguity. All right? Yeah. Okay, so that's a good, very good. So here we go. Find the largest area enclosed. So that's sort of a trick question, isn't it? So there are various. That's a good thing to ask. That's sort of a trick question. Why? Because according to the rules, we're trapped between the two maxima and something which is strictly below. So in other words, one answer to this question would be, and this is the answer that I would probably give, is 1/16. But that's not really true, because that's only in the limit. As x goes to 0, or as x goes to minus. And if you like, most is when you've only got one square, which it breaks the rules of the problem. All right? So essentially, it's a trick question. Right? But I would answer it this way, because that's the most interesting part of the answer, which is that it's 1/16, and it occurs really when one of the squares disappears to nothingness. All right. So now, let's do another example here. And I just want to illustrate sort of the second style or the second type of question. Yeah. So the question is, since the question was, what was the largest area, why did we find the least area? And the reason is that when we go about our procedure of looking for the least or the most, we will automatically find both. Because we don't know which one is which until we compare values. And actually, it's much more to your advantage to figure out that one, both the maximum and the minimum, whenever you answer such a question. Because otherwise, you won't understand the behavior of the function very well. So So the question, we started out with one question, we answered both, we answered two questions. We answered the question what the largest and the smallest value is. Yes, one can also use, the question is, can we use the second derivative test? And the answer is yes, we can. In fact, you can actually also stare at this and see that it's a sum of squares, so it's always curving up. It's a parabola with a positive second coefficient. So you can differentiate this twice. If you do, you'll get an 8 plus another 8, and you get a 16th. So the second derivative is 1/16, is 1/4. And that's an acceptable way of figuring out. I'll mention the second derivative test again in this second example. So let me talk about a second example. So again, this is going to be another question. The question is, when I say minimum or maximum point, which will I mean? Yeah, so that's the question. I just repeated the question. So the question is, when I say minimum point, what will I mean? Okay? And the answer is that for the purposes of this class, I will probably avoid saying that, but I will say probably where is the minimum achieved, just in order to avoid that. If I actually said it, I often am referring to the graph, and I mean this. And in fact, when you get your little review for the second exam, I'll say exactly that on the review sheet. Okay? And I'll make this very clear when you're doing this. However, I just want to prepare you for the fact that in real life, and even me when I'm talking colloquially, when I say what's the minimum point of something, I might actually be mixing it up with this other notion here. All right? Okay, so let's do another example. So this is an example to get us used to the notion of constraints. So consider a box without a top. Or if you like, we're going to find a box without a top with least surface area for a fixed volume. All right? Find the box without a top with least surface area for a fixed volume. The procedure for working this out is the following. You make this diagram, and you set up the variables. Right, in this case, we're going to have 4 names of variables. All right? We have 4 letters that we have to choose, and we'll choose them in a kind of standard way. All right? So first, I have to tell you one more thing, which is something that we could calculate separately, but I'm just going to give it to you in advance, which is that it turns out that the best box has a square bottom. And that's going to get rid of one of our variables for us. So it's got a square bottom, and so let's draw a picture of it. So here's our box. Well, I guess that goes down like this. Almost. Maybe I should get a little farther down. All right, so here's our box. That's correct. All right, so now what about the dimensions of this box? Well, this is going to be x, and this is very foreshortened, but it's also x. The bottom is x by x. It's the same dimensions. And then the vertical dimension is y. Okay? So far, so good. Now I promised you 2 more letter names. I want to compute the volume. All right? The volume is the base is x squared, and height is y, so there's the volume. And then the area is the area of the bottom, which is x squared. That's the bottom. And then there are the four sides. And the four sides are rectangles of dimensions x, y, so it's 4xy. All right, so these are the sides. And remember, there's no top. So that's our set. So now, the difference between this problem and the last problem is that there are two variables floating around, namely x and y, which are not determined, but there's what's called a constraint here. Namely, we fixed the relationship between x and y. And so that means that we can solve for y in terms of x. So y is equal to b divided by x squared. And then we can plug that into the formula for a. So here we have a, which is x squared plus 4x times b over x squared. Question? Yeah. The question is, well, you need to know this intuitively? No, that's something that I would have to get to. I mean, it's actually true that a lot of things, the correct answer is something symmetric. In this last problem, the minimum turned out to be exactly halfway in between because there were sort of equal demands from the two sides. And similarly here, what happens is if you elongate one side, you get less. It actually is involved with a two-variable problem, namely if you have a rectangle, you have a certain amount of length associated with it. What's the optimal thing you can do with that? But I want, in other words, the optimal rectangle, the least perimeter rectangle turns out to be square. That's a little sub-problem that leads you to this square bottom. So that would have been a separate max-min problem, which I'm skipping because I want to do this slightly more interesting. All right? Okay, so now, here's our formula for A, and now I want to follow the same procedure as before. And we can look for the critical point, or points. So let's take a look. So again, A is x squared plus 4b over x. And a prime is 2x minus 4b over x squared. So if we set that equal to 0, we get 2x equals 2b over x squared. So 2x cubed, well, how did that happen to change it to 2? Interesting. So that's wrong, okay? Right, so this is x cubed is equal to 2b, right? And so x is equal to 2 to the 1/3 b to the 1/3. All right, so this is the critical point. So we are not done, right? We're not done because we don't even know whether this is going to give us the worst box or the best box from this point of view. One uses the most air surface area or the least. So let's check the ends right away. See what's happening. So can somebody tell me what the end values of x are? Where does x range from? What's the smallest? Yeah. Okay, their claim was the largest x could be root a because somehow there's this x squared here and you can't get any further past that. But there's a key feature here of this problem, which is that A is variable. The only thing that's fixed in the problem is V. Okay? So if V is fixed, what do you know about X? Yeah. X is greater than 0. Yeah, the lower end point, that's safe, because that has to do geometrically with the fact that we don't have any boxes with negative dimensions. That would be refused by the post office, definitely. Get over and above the empty top, so we're accepted. It's true that X is less than square root of V over Y, so that's using this relationship. But notice that Y is equal to V over X squared. So 0 to infinity, I just got to guess there over here. That's right. Here's the upper limit. So this is really important to realize. This is most problems. Most problems, the variable, if it doesn't have a limitation, usually just goes out to infinity. And infinity is a very important end for the problem. It's usually an easy end to the problem, too. All right? So there's the possibility that if we push all the way down to X equals 0, we'll get a better box. It'll be a very strange box, a little bit like our vanishing enclosure, and maybe an infinitely long box, also a very inconvenient one, might be the best box. We'll have to see. All right? So let's just take a look at what happens. So we're looking at A at 0 plus, right? And that's X squared plus 4A over X with X at 0 plus. So what happens to that? Notice right here. This is going to infinity, all right? So this is infinite. So that turns out to be a bad box. All right, let's take a look at the other end. So this is X squared plus 4B over X. X going to infinity. And again, this term here means that this thing is infinite. So the shape of this thing, I'll draw this tiny little schematic diagram over here. The shape of this thing is like this. Right? And so when we find that one turnaround point, which happened to be at this strange point 2 to the 1/3, sorry, V to the 1/3, that is going to be the minimum. All right? So we just discovered that it's the minimum, which is just what we were hoping for. This is going to be the optimal box. Now, since you asked earlier, and since it's worth checking this as well, let's also check an alternative justification. So an alternative to checking ends is the second derivative test. I do not recommend the second derivative test. I try my best when giving problems to make it really hard to apply the second derivative test. But in this example, the function is simple enough so that it's perfectly okay. If you take the derivative here, remember, this was, whatever it was, 2x minus 4b over x squared. If I take the second derivative, it's 2 plus 8b over x cubed. And that's positive. So this thing is concave up. And that's consistent with its being a critical point to me. Is a minimum point. See how I almost said is a min as opposed to minimum point. So watch out. Yes? You're one step ahead of me. The question is this the answer to the question of we have to give y and a and so on and so forth? So again, I want to, this is something that I want to emphasize and take my time with right now. because it depends what kind of real-life problem you're answering and what kind of answer is appropriate. So far, we've found the critical point. We haven't found the critical value. We haven't found the dimensions of the box. Okay? So we're going to spend a little bit more time on this exactly in order to address these questions. So first of all, the value of y. So far we have x is 2 to the 1/3, b to the 1/3. And certainly if you're going to build the box, you also want to know what the y value is. The y value is going to be, let's see, well, it's v over x squared, so that's v divided by 2 to the 1/3, v to the 1/3 squared, which comes out to be 2 to the minus 2/3, v to the 1/3. Okay? So there's the y value. On top of that, we can figure out the value of a. All right? So that's also a perfectly reasonable part of the answer. Depending on what one is interested in, you might hear how much money it's going to cost you to build this box, this optimal box. And so you plug in the value of a. So a, let's see, is up here. It's x squared plus 4v over x. So that's going to be 2 to the 1/3 v to the 1/3 squared plus 4v divided by 2 to the 1/3 v to the 1/3. All right? And if you work that all out, what you get turns out to be 3 times 2 to the 1/3 v to the 2/3. All right? So if you like, one way of answering this question is these three things. That would be the minimum point corresponding to the graph. That would be the answer to this question. But the reason why I'm carrying it out in such detail is I want to show you that there are much more meaningful ways of answering this question. So let me explain that. Some more meaningful answers here. The first more meaningful answer is the following sort of idea. Simply, they were known as dimensionless variables. So the first thing that you notice is the scaling law. A divided by v to the 2/3 is the thing that's a dimensionless quantity. That happens to be 3 times 2 to the 1/3. Okay? So that's one thing. If you want to expand the volume, you'll have to expand the area by the 2/3 power of the volume. And if you think of the area as being in, say, square inches, and the volume of the box is being in cubic inches, then you can see that this is a dimensionless quantity, and you have a dimensionless number here, which is a characteristic independent of what A and V were. The other dimensionless quantity is the ratio of y to x to y. Right? So again, that's inches divided by inches. And it's 2 to the 1/3 v to the 1/3 divided by 2 to the minus 2/3 v to the 1/3, which happens to be 2. All right? So this is actually the best answer to the question. And it shows you that the box is a 2-to-1 box. If this is 2 and this is 1, that's the good box. Right? This is just the shape, if you like. And it's the optimal shape. And certainly, aesthetically, that's the cleanest answer to the question. All right, there was a question right here. Yes.
Could you repeat that after me?
would we have gotten the answer if we weren't told that the problem was squared? The answer is yes in 1802 with multivariable. You would have to have 3 letters here, an X, a Y, and a Z if you like. And then you have to work with all 3 of them. All right? So I've separated it out into one. There's a separate one variable problem you can do for the base, and then there's a second one variable problem for this other thing. And it's just 2 consecutive one variable problems that solve the multivariable problem. Or as I say in multivariable calculus, you can just do it all in one step. Yeah. Why did I divide x by y? Rather than y by x or any. So again, what I was aiming for was dimensionless quantities. So x and y are measured in the same units, and also the proportions of the box. So that's another word for this is proportions. Are something that's universal, it's independent of the volume V. It's something you can say about any box at any scale, whether it be, something like Christo, in common, maybe we'll get here to some fancy the proportions is with geometric problems typically when there's a scale into the problem where the answer is the same at small scales and at large scales, this is capturing that. So that's why the ratios are what's capturing that. And that's why it's aesthetically the nicest thing to ask. Okay? Unfortunately, this number is a really obscure number, so it doesn't. If the question is, what does this tell us? The only thing that I want to emphasize is what's on the left-hand side here, which is it's the area to the 2/3 power of the volume, so it's a dimensionless quantity. It happens to be this. If you do this, for example, in general with planar diagrams, circumference area is a bad ratio to take. What you want to take is the square of circumference to area, because the square of circumference has the same dimensions, that is, say, inches squared to area, which is the square inches. So again, it's these dimensionless quantities that you want to hook up. And those are the ones that will have universal properties. The most famous of these is that the circle encloses the most area for its circumference. And again, that's only true if you measure where you take the square of the circumference. You do the units correctly. Right? Okay. Anyway, okay, so we're here. We've got a shape, we've got an answer to this question. And I now want to do this problem. Well, let's put it this way. I wanted to do this problem by a different method. I think I'll take the time to do it. So I want to do this problem by a slightly different method. So here's example 2 by implicit differentiation. So the same example, but now I'm going to do it by implicit differentiation. And I'll tell you the advantages and the disadvantages to this method here. So the situation is we have to start the same way. So here was the starting place of the problem. All right? And we're aiming, the goal was the minimum of A with V constant. So this was the situation that we were in. And now, what I want to do is just differentiate. All right? The function y is implicitly a function of x, so I can differentiate the first expression. And that yields 0 is equal to 2xy plus x squared y prime. Right? So this is giving me my implicit formula for y prime. So y prime is equal to minus 2xy divided by x squared. Or in other words, minus 2y divided by x. And then I also have the derivative of a with respect to x. Now, you may notice I'm not using primes quite as much because all of the variables are varying, so here I'm emphasizing that it's the differentiations with respect to the variable x. And this becomes 2x plus 4y plus 4x y prime. So again, this is using the product rule. And now I can plug in for what y prime is, which is right above. So this is 2x plus 4y plus 4x times minus 2y over x. Okay? And that's equal to 0. And so let's gather that together. So what do we have? We have 2x plus 4y, and then altogether this is 8 minus 8y. So that's the same thing as 2x is equal to 4y. Right, the minus 4y goes to the other side. And so x over y is equal to 2. So this, I claim, well, so you have to decide for yourself, but I find that this is faster. All right? It's faster, and also it gets to the heart of the matter, which is the scale invariant proportions, which is basically also nicer. So it gets to the nicer answer also. So those are the advantages that this has. So it's faster, and it gets to this, I'm going to call it nicer. And the disadvantage is did not check whether this critical is a max min or e. Okay, so we didn't quite finish the problem, but we got to the answer very fast. Yeah, question. How would you check it? Well, so it gives you a candidate. The answer is, so the question is, how would you check it? The answer is that for this particular problem, the only way to do it is to do something like this. All right, so in other words, it doesn't save you that much time. But with many, many examples, you actually can tell immediately that at the two ends the thing is say 0, and inside it's positive, things like that. So in many, many cases, this is just as good. All right? Okay. So now I'm going to change subjects here, but the subject that I'm going to talk about next is very, very closely linked. Namely, I talked about implicit differentiation. Now we're going to just talk about dealing with lots of variables and rates that change. So essentially, we're going to talk about the same type of thing. So I'm going to tell you about a subject which is called related rates, which is really just another excuse for getting used to setting up variables and equations. So here we go, related rates. And I'm going to illustrate this with one example today, one tomorrow. So here's my example for today. So here, again, this is going to be a police conflict. This is going to be a work conflict. And sorry, no one's here. No police. Well, they're police in the story, but they're not present. But I'm going to draw it immediately with the diagram because I'm going to save us the trouble. Although, you know, the point here is to get from the words to the diagram. Okay, so you have the police, and they're 30 feet from the road. And here's the road. And you're coming along here in your let's see, in your car going in this direction here. And the police have radar, which is bouncing off of your car. And what they read off is that that you're 50 feet away. All right? They also know that you're approaching along the line of the radar at a rate of 80 feet per second. Okay? Now, the question is, are you speeding? Okay? That's the question. So when you're speeding, by the way, 95 feet per second is about 65 miles per hour. So that's the threshold here. So what I want to do now is show you how you set up a problem like this. All right? This distance is 50. This is 30. And because it's the distance to a straight line, we know that this is a right angle. So we know that this is a right triangle. And this is set up to be the right triangle, which is an easy one, a 3, 4, 5 right triangle, just so we can do the computations easily. All right? So now the question is, how do we put the letters in to make this problem work, to figure out what the rate of change is? Now let me explain that right now, and we will actually do the computation next time. So the first thing is, you have to understand what's changing and what's not. And we're going to use t for time in seconds. Okay? And now, an important distance here is the distance to this foot of this perpendicular. So I'm going to name that x. All right, I'm going to give that letter x. Now, x is varying. The reason why we need a letter for it as opposed to 40 is that it's going to have a rate of change with respect to t. And in fact, it's related to, the question is whether dx dt is faster or slower than 95. Okay? So that's the thing that's varying. Now there's something else that's varying. This distance here is also varying, so we need a letter for that. We do not need a letter for this, because it's never changing. We're assuming the police are parked. They're not ready to roar out and catch you just yet. And they're certainly not in motion when they've got the radar guns aimed at you. So we need to know something about the sociology and style of police when they're, okay? So you need to know things about the real world. Now the last bit is, what about this 80 here? So this is how fast you're approaching. Now that's measured along the radar gun. I claim that that's d by dt of this quantity here. So this d is also changing. That's why we need a letter for it too. So next time we'll just put that all together and compute dx by dt.
Okay, now you have actually reviewed 3 specific examples on Max and getting ready for related rate applications. Well, basically, it's a little bit interesting because you finished the midterm yesterday, and these are actual part of the midterm. But I didn't set questions here, except one question, which is taken directly from the example of the textbook. But I do not know if you enjoy that. I'm going to check how you take advantage of things like this. The only thing that I would like to make sure is that I want to create an impression of you. A lot of those things we did not discuss along the way, because I just want to make sure that you have a very easy part to review those techniques, okay? Maybe the technique, but here there's a lot of thinking behind. And when you look at the specific things explained by David Joseph here, you can see that a lot of time he has to restrain from telling the students why this is so, giving them a way to see themselves. For example, in the previous example here, we used 2 methods to show to the student how to solve the problem. And the second method is implicit differentiations. But what's the disadvantage of that? If you go for the critical method, you will not have a chance to check for the critical point. But what does it mean? When you did not check for the critical point, do you have an idea whether it's a maximum or minimum one, or earlier when we study the videos in Khan's Academy, if it is not one of these, could that be undefined? So I think it's very important that I provide this review period for you, because my target is for you to have solid foundations to go into integrations, and also it's important for your final exam. Alright, so the next thing I would like to show you a little bit is the momentum rule, because in chapter 4, that is the next topic we need to discuss. And I would like you to go back when you have finished your days in class, come back to week number 9 and day number 18 to script display, and you will be brought to the concept economies, explanations of this rule. Okay, I'm going to show you only 8 minutes of this, just to give you enough of the nomenclature rules, okay? This is sound and class, alright? Let's see.
Most of what we do early on,
Wait.
we first learn about calculus.
Okay, anyway.
Is to use limits. We use limits to figure out derivatives of functions. In fact, the definition of a derivative uses the notion of a limit. It's the slope around the point as we take the limit of points closer to the point in question. You can that many times. In this video, we're going to do, we're going to do it in the opposite direction. We're going to use derivatives. We're going to use derivatives to figure out limits.
You see it
In particular, limits that end up in indeterminate form. And when I say by indeterminate form, I mean that when we just take the limit as it is, we end up with something like 0 over 0, or infinity over infinity, or negative infinity over infinity, maybe negative infinity over negative infinity, or positive infinity over negative infinity. All of these are indeterminate, undefined forms. And to do that, we're going to use L'Hopital's rule. L'Hopital's rule. L'Hopital's rule. In this video, I'm just going to show you what L'Hopital's rule says, how to apply it. It's fairly straightforward. It's actually a very useful tool sometimes. Mathematicians can ask you to find a difficult limit that when you just plug the numbers in, you get something like this. L'Hopital's rule is normally what they are testing you for. And in a future video, I might prove it. That gets a little bit more involved. The application is actually reasonably straightforward. So L'Hopital's rule tells us that if we have, and I'll do it in abstract form first, but I think when I show you the example, it'll all be made clear. That if the limit as x approaches c of f of x is equal to 0, which is also, so that this is equal to 0, and the limit as x approaches c of g of x is equal to 0, and, this is another and the limit as x approaches c of f prime of x over g prime of x exists and it equals L, then, so all of these conditions have to be met. This is the indeterminate form of 0 over 0, so this is the first case. Then we can say that the limit as x approaches c of f of x over g of x is also going to be equal to L. So this might seem a little bit bizarre to you right now. And I'm actually going to write the other cases, and I'll do an example. We'll do multiple examples. The examples are going to make it all clear. So this is the first case. And the example we're going to do is actually going to be an example of this case. Now the other case is if the limit as x approaches c of f of x is equal to positive, or negative infinity, and the limit as x approaches c of g of x is equal to positive or negative infinity, and the limit of, I guess you could say, the quotient of the derivatives exists, and the limit we can make this same statement again. And we can make this exact statement again. Just copy that out. And this again. Edit, copy, and then paste. So either of these two situations, just to kind of make sure you understand what you're looking at. This is the situation where if you just try to evaluate this limit right here, you're going to get f of c, which is 0, or the limit as x approaches c of f of x, over the limit as x approaches c of g of x. That's going to give you 0 over 0. And so you say, hey, I don't know what that limit is. This says, well, look, if this limit exists, I could take the derivative of each of these functions and then try to evaluate that limit. And if I get a number, if that exists, then they're going to be the same limit. This is the situation where when we take the limit, we get infinity over infinity, or negative infinity, or positive infinity, or positive or negative infinity. So these are the two indeterminate forms. And to make it all clear, let me just show you an example, because I think this will make things a lot more clear. So let's say we are trying to find, the limit, this is one color, do it in color. Let's say we wanted to find the limit as x approaches 0 of sine of x over x. Now, if we just view this, if we just try to evaluate it at 0 or take the limit as we approach 0 of each of these functions, we're going to get something that looks like 0 over 0. Sine of 0 is 0, or the limit as x approaches 0 of sine of x is 0, and obviously as x approaches 0 of x, that's also going to be 0. So this is our indeterminate form. And if you want to think about it, this is our f of x. That f of x right there is the sine of x. And our g of x, this g of x right there for this first case, is the x. Right? G of x is equal to x, and f of x is equal to sine of x. And notice, well, we definitely know that this meets the first two constraints. The limit as x, and in this case c, is 0. The limit as x approaches 0 of sine of x is 0, and the limit as x approaches 0 of x is also equal to 0. So we get our indeterminate form. So let's see at least whether this limit even exists. If we take the derivative of f of x, that over the derivative of g of x, take that the limit as x approaches 0 in this case, x approaches 0, that's our c. Let's see if this limit exists. So I'll do that in blue. So let me write the derivatives of the two functions. So f prime of x, if f of x is sine of x, what's f prime of x? It's just cosine of x. Times. And if g of x is x, what is g prime of x? It's just derivative of x is just 1. So let's try to take the limit. Let's try to take the limit as x approaches 0 of f prime of x over g prime of x, over their derivatives. That's going to be the limit as x approaches 0 of cosine of x over 1. And this, over 1. And this is pretty straightforward. What is this going to be? Well, as x approaches 0 of cosine of x, that's going to be equal to 1. That's equal to 1, and obviously the limit is x approaches 0 of 1. That's also going to be equal to 1. So in this situation, we just saw that the limit as x approaches, our c in this case is 0, as x approaches 0 of f prime of x over g prime of x is equal to 1. This limit exists, and it equals 1, so we've met all of the conditions. This is the case we're dealing with. Limit as x approaches 0 of sine of x is equal to 0. Limit as x approaches 0 of x is also equal to 0. The limit of the derivative of sine of x over the derivative of x, which is cosine of x over 1, we found this to be equal to 1. So all of these top conditions are met. So then we know this must be the case, that the limit as x approaches 0 of sine of x over x must be equal to 1. It must be the same limit as this value right here. We'll take the derivative of the f of x and of the g of x. I'll do more examples in the next few videos, and I'll make it a lot more clear.
Okay, this is the first view into the logical root. And next week, when you come back, we will come to discuss the mean value theorem, which is very important. Looks like very simple, but in chapter 4. Okay, allow me to take attendance for today. And you will be informed of what homework problems to do for the next week's homework by tomorrow. Okay, so just keep yourself updated with the relevant problem. Vicky, thank you. Terry, thank you. Eden, thank you. Jason, thank you. Kirkwood, thank you. Ron, thank you. Amy, thank you. Susie, thank you. Bob, thank you. Vivian, thank you. Strong, thank you. Isho, thank you. Cindy, not here today. Shu, yes. Pete, thank you. Elaine, thank you. Kent, thank you. Alphys, not here. Anson is excused. Caesar, thank you. Alex, thank you. Ina, thank you. Gotcha, thank you. Simha, are you here? No. Kim, thank you. Simon, not here. Okay. William, excused. Sting is here. Esther, thank you. Ida, thank you. Ning, thank you. Lago, thank you. Flora is not here today. Okay. Amber is here. Jackie, yes, thank you. Kay, not here. Alright, thank you very much. Is it difficult for the midterm? Yes.
So please be easier.
Easier. Okay. Next time we can choose 10. Thank you very much for your support. Work on. Okay? Great. You enjoyed it? That's it for today's MATB110, Section 1, Calculus 1, date number 18, March the 19th, 2015. Until next week, stay tuned.